Okay, good morning. So I think that last time we were computing this quantity, I of t, which is the susceptibility, which, if you want, is the response of our system to an external magnetic field. So how does the magnetization of the material responds to reacts to an external magnetic field. So it's derivative, you know. So this is a function of t and h, and this is the partial derivative of m with respect to h, fixed temperature. And for m, we have used the implicit equation that we have derived in mean field. Okay. Now, I think that we have computed already the limit for also the chi t of t h equals 0 for t approaching Tc from above, and I think we said that this is equal to 1 divided by kb Tc, here t, where t is defined to be basically the deviation with respect to the critical temperature. Okay, so t equals 0 means that we are at the critical temperature. So you see here that there is a divergence of the susceptibility when we are close to the critical temperature as 1 over modulus of t. Okay. Now, in principle, what happens below Tc could be completely different, but actually when doing the calculation, and we try to do it now, we get the same behavior, just with a different coefficient. Okay, but the divergence is present also there. Okay, and so let's try to do it. The starting point is the complete formula for the chi t, which was this one, theta divided by the square of beta times h plus and epsilon q, and then we got minus. Well, maybe let me write this. Okay, this was the general expression. And here there was a minus Tc divided by T. And let me see how to do it. So let's see the behavior of this quantity. Let's compute it for h equals 0, because this is what we have done last time. This was chi t 0, and therefore the chi t is equal to theta divided by cos hyperbolic square of beta. This h is equal to 0, and beta times epsilon q, beta m epsilon q is m times Tc divided by T. Okay, so this is the starting point that we have used also last time. Okay. Okay, good. So now, last time, what we did is actually was to consider the fact that when we are above C, the magnetization M is equal to 0, and therefore the expression was found very easily. Now we are below C, for T approaching TC from below, and therefore we have to use an expansion there. We know that the magnetization in any case goes to 0 when T approaches TC, and so we can expand by using the cos, by using this cos h of x for small x is 1 plus x squared divided by 2 plus other terms. Okay. So we put this in here, and then this is equal when T approaches TC from below to beta, and here at the denominator we have 1 plus well, this one, so 1 half and TC divided by T squared minus TC divided by T. Okay. And I think that there is another square here because here the cosine is squared and then is minus T divided by T. Okay, so now it's a matter of doing a calculation, and let us remember that M, when we are close to the critical temperature and from below, was equal, well, almost equal to plus minus square root of 3 that we derived last time, no? Okay, so now we introduce this expression there, and basically it's a matter of doing the calculation. So chi t equal to beta. We have here 1 plus 1 half, and here m tc divided by t. This is squared, so we have tc divided by t squared times m squared, which means 3t, and everything is squared, minus tc divided by t equal. Now, okay, we can neglect, since t is small, or is t here, we can neglect the second order in t. So this is beta 1 plus tc divided by t squared. Then I have a 3 t and minus tc divided by t. Vediamo se è giusto. 1 plus 3t minus tc divided by t. I think it's correct. Not tc. Okay. Now, okay, let's elaborate a little bit this one. So this is beta. 1 plus this guy is what is this? T minus tc divided by t plus 3t and tc divided by t squared. And t 3t, quello va bene, tc, t va bene. Yeah. So then let's multiply this times tc and divide divided by Tc. Now this guy here is minus T and Tc divided by T. So let me write down after once. So since we are approaching T from below, this guy here is actually minus T minus Tc divided by Tc. Okay, so then this is minus so the chi T is equal to beta. And here I have T divided by T, and then I have a minus T. What this way, okay. And then I have plus 3 divided by T. Okay, now I think it's done because basically we can, well, since we are close to Tc, this is equal to 1. This is also equal to 1. Therefore, I have 3t minus 1. Beta divided by 2t. And actually, also the beta will cancel because, okay, first of all, we can do this. Let me see. I can do it. Facciamo prima questo. So here I have beta, and then I have t that I can collect, and Tc divided by t. Here I have 3 Tc divided by t minus 1, and therefore at the end, as I said before, so this is close to 1, and so yeah, I have 1 divided by kBt modulus of t is t divided by t, and here I have 2. Finally, T is 1 divided by 2 kb Tc, and then modulus of t is for t approaching Tc. Okay. So now the calculation is complete. So we have the behavior above Tc and the behavior below Tc. So the critical, so the behavior of the susceptibility at the critical temperature is completed completely. So the chi of t scales as 1 over kb Tc t for t going to Tc from above, and 1 divided by 2 kb Tc T approaching Tc from below. Okay, so we can make a plot of this susceptibility, and of course we have a singularity there. This is the following. So we can make a plot of time of t as a function of the temperature. Here at Tc we have a singularity. Okay, with different coefficients. What is important here is the scaling as 1 over the modulus of t. Okay. When we have this kind of divergences, we have commented other times. This is a phenomenon which is related to the phase transitions, and actually, as usual, one should say that those divergences are present in the thermodynamical limit for finite systems that are not divergences. Okay. Now, if, but I'm not going to do it, but if H is different from 0, there's no divergence. Because actually, when H is different from 0, this is not a phase transition anymore. It has a smooth behavior, as we will see in a moment. Okay. Anyway, we started to compute. Let me anticipate this. These exponents of t, which are called the critical exponents, and we have actually seen two of them. So I will comment this later. And what is important that the exponents of these different quantities can fall in a certain class of universality. That is something that you will do not here because we are almost done the course. But it's interesting to see that several different systems can behave at the critical point in a similar way. So with the same exponents when working, let's say computing these quantities as a function of T, which is the deviation from the critical temperature. So this is a high-dimensional quantity. Okay. Something that we have seen also, we have commented also for the case of the Van der Waals gas situation. But I will comment this later. Now, another thing that it's interesting to do is to see the behavior of the Helmholtz free energy when we are close to the phase transition, close to the critical point, because in that case you can clearly see what's going to happen when we have a phase transition in terms of Helmholtz free energy. So let's try to compute it. So A, I don't know if I'm going to compute A or better A divided by N, which is the same. And okay, this was done already in this calculation. This was epsilon Q m squared divided by 2. Then there was a minus kBt, the log of 2 cosinus, etc. So it's a minus kBt log of 2, which is a constant, which does not depend on m. And then there is a minus kBt log of cos h of theta epsilon q. Okay. Now this was derived last time. Okay, in the midfield approximation. Derived in midfield approximation. Now what we are going to do is to make an expansion around m equals 0, which means that when we are close to Tc, and so we are going to expand this function here around Tc. We know that m is approaching 0. Well, actually, this equal to 0 identically for T larger than Tc. When we are below Tc, m is going to 0, okay, as a limit. Okay, so let's make this expansion. A divided by n is equal to epsilon q m squared divided by 2, and this is minus kBt log of 2 minus kBt. And here we're going to expand this log, and we use this formula. Put it here. Log of cos h x is equal to x squared divided by 2 minus x 4 divided by plus And so here I will have minus kBt. Then I have this quantity divided by 2. So beta epsilon and q squared. Then I have a minus with a minus here plus kBt divided by 12, and same quantity beta epsilon and q to the power of 4 times. Okay. Now, okay, it's a matter of elaborate a little bit on this. Let me see, the most important part is the following. So kBt log of 2 there. Then we have this term that I can collect divided by 2 and t. Yeah, okay, so let's write this in the following way. So I have, let me collect epsilon q m squared divided by 2. And here I will have 1. Then I have a minus epsilon q m squared. So the q, so the m squared is already collected. So then I should get a beta squared kBt divided by 2, beta squared the kBt divided by 2, and then I have an epsilon and q, and sorry, the q is here, so then yes, I should have another q there, and the m squared is collected, and epsilon, I should be this, okay? Let me check. Epsilon q, and the 2, sorry, the 2 is not there because I have collected the 2 here. And beta squared kBt means 1 over kBt, actually. kBt. Okay, epsilon q divided by kBt. Plus, so here let me do, it's not important to keep all these quantities that in any case are positive. So let me just write it as m to the power of 4, which is this guy here, times constant b, or b is positive. Well, in this case, b is kBt divided by 12, and there is a beta to the power of 4, epsilon to the power of 4, and q to the power of 4. This is not important, but this is a constant. But anyway, the behavior is m to the power of 4 times a certain constant that is positive. Now this is equal to minus kBt log of 2 plus epsilon q m squared, and maybe here. Okay, now let's leave it for the moment like this. Epsilon q m squared divided by 2, and here I have epsilon q divided by kb is just Tc, as we saw last time. Therefore, here I will have T minus Tc, and I have a T here. Okay. Plus m to the power of 4 times b. So again, this is another quantity which is anyway it's constant, epsilon q divided by 2t. Therefore, the expression that we have for this behavior of A close to Tc is the following. So A divided by n close to Tc is equal to, okay, this term, which is an just constant at fixed temperature. It's not important. Then I have a quantity here that is a certain number A, which is epsilon q divided by 2c, which in any case is positive. Then I have t minus dc, n squared, plus b, which is another positive constant, m to the power of 4. Okay, so this is a very interesting formula, actually, that you will, it's a paradigm of what happens in a phase transition. Below Tc and at Tc, because we can now make a plot of A divided by n, so the Helmholtz free energy per particle as a function of n and at different values of the temperature. So we can make the following plot. So A divided by n as a function of the magnetization per particle m. And let's plot it for t larger than Tc. We don't know here what's the value of m, but we can actually derive it because I'm not using the implicit equation for m, but actually we can derive it in the following way. If we make this plot, now this coefficient is positive because we are above Tc, and these are quartic in m. And if you make a plot, apart from this term, which is just a constant, you will get something like this. Okay, where you see that A divided by n is minimized for m equal to 0. Okay, and we know that if we work at fixed temperature and well, fixed number of particles and fixed volume, the second principle of thermodynamics tells me that I have to minimize the Helmholtz free energy. So that means that the solution that minimizes A is the correct one, is the one that is realized in nature at the thermodynamical equilibrium. Okay, so m equals 0 is the only solution, or the only possibility for t larger than Tc. Okay, because it minimizes the Helmholtz free energy, and so because of the second principle of thermodynamics, this is the state that will be reached. Now, what happens when T instead is equal to Tc? Now, here this term will disappear, and therefore we will have a quartic again in M. Now the shape is more or less similar to this one, but it's somehow the higher order derivatives of m are equal to 0 also, no? Because here we have that A divided by n scales as something which is a constant and n to the power of 4, and therefore the solution is still m equals 0 that minimizes the free energy. Correct one. but here we have also that the higher order derivatives of m are equal to 0. Okay, so somehow it is here. Okay. Now the magic occurs when t is smaller than tc. You can try to make a plot also with mathematical of this function. This is a quartic with a positive term here, which multiplies the highest power of m. Whereas here now, if t is smaller than tc, it is negative. And if you make a plot of this, now it's very interesting because what you get is the following. For t smaller than tc, now that's the interesting part. You will get a plot like this one. Where now you see that there are 3 points for which the derivative of a with respect to m is equal to 0. So there are extrema for m, but now m equal to 0 corresponds to a local maximum of a. Therefore, this configuration is not the one which is realized now in equilibrium, because the second principle of thermodynamics tells me that I have to minimize this quantity. And the way to minimize this quantity is to go either here, let's call it minus m0, or here, plus mt. Okay? Therefore, one of these two solutions is the one that is realized in thermodynamical equilibrium, and therefore we have spontaneous magnetization. Okay? So this corresponds to a spontaneous magnetization. Which can occur either with a positive value of m0 or a negative value. Or minus m0, which is smaller than 0. Okay? This we do not have any preference, so these two minima are degenerate, at least in this situation. Okay? So if you want the physics of the phase transition is basically qualitatively hidden, well, not even hidden, but qualitatively described by this plot, okay, that you will see in many other situations, because this is paradigmatic, though it's found in a very simple model, which is the Ising model. This kind of behavior of here is the Helmholtz free energy, in other contexts would be a potential, is paradigmatic for the phase transition, in the sense that the fact that you developed those two minima then allows you to find positive, well, finite values for m0, or in other case, other quantities such as what happens in the, now if you have started to do the Higgs bosons, I don't know, you have seen already. Have you seen something like this? Yeah, okay. So it's somehow the same mechanism, okay? In that case, what you minimize the potential of the field, whereas here is the Helmholtz free energy. Okay, so this is a spontaneous magnetization, which corresponds to spontaneous symmetry breaking, because in any case, both here and here you are picking up a preferred direction, which is a plus or minus, because we just have two directions in this model, and occurs at t for t smaller than tc. Okay, now what happens? So another thing that we can learn from this story is that we can get m by minimizing the Helmholtz free energy. Okay, as it should be, because we are always, we can always rely on the second principle of thermodynamics. Now we can make a sketch of what happens when working with finite value of the magnetic field, external magnetic field. You can just sketch the behavior. So what happens for H now different from 0? Now in the expression of A divided by N, there are all the terms that we had before, but there is a logarithm minus the logarithm of cos H of beta times epsilon plus m epsilon q. Okay. And then if I do the derivatives of this quantity with respect to m, I have all the other terms. Well, actually here I just have the epsilon qm squared and the minus kbt log of 2. But here I will have minus, here again the cos h of beta h plus m epsilon q. Then I have to derive the cos, which is a sinus h of beta epsilon plus m epsilon q. And then I have the derivative of this guy with respect to him, which is beta epsilon q. Beta epsilon q. And vediamo un attimino, scusate. So, okay. When, okay, this is just to get the coefficient actually, that we compute for m equal to 0. But when expanding this guy around, m equal to 0 as before, we get this term to the power of 2 and then to the power of 4. And by neglecting the higher order term, we get the well, the square of these, which will contain, apart from a constant, will contain a linear term in m and h. Okay, so we get something that is proportional to m because of this. Okay, so just to be more clear, the log of cos h of x was equal to x squared divided by 2 minus x to the power of 4 divided by 12. Right. And here, when I do this, I get beta h plus m epsilon q squared divided by 2, and the same quantity h plus m epsilon q now to the power of 4 and divided by 12. Now you see when making this calculation that I will get a term which contains beta h squared divided by 2. Then I have the square of m that I had also before. And also I have a linear term now, which is the product of m h epsilon cube beta. So with respect to the previous calculation, so I'm not going to do the calculation again, I have an additional term which is proportional to m. So it's linear in m. Okay, when I have an external magnetic field, that's the story. So, and what is the coefficient of this? Again, without doing the calculation, because it's just a matter of doing derivatives, blah, 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 one can realize that in the linear term in M, will be something like, let me see, M times sine h of beta h divided by cos h of beta h, which comes from here. This expression is correct. Then I will have to expand, and computing this guy at m equals 0, I get this factor, okay? Which is can be written as I'm sorry, here there is an additional minus here coming from this. So it's a minus c times m, where c is positive when h is positive, and negative when well, it has the same sign of h basically. Okay. Or c positive h larger than 0, and c is negative h smaller than 0, because I have a sign here which is odd in h. Now, what happens in the plot? I'm sketching this derivation because it's a little bit lengthy, and in a way, just what is important just to see that we have a linear term and how does the plot change in this linear term. Now, this quartic will not contain now only M4, M2, and a constant. It will contain also linear term in M, which is beta here. And if you make a plot now, the situation is a little bit different, because you get for t larger than Tc and h positive, you will get something like this. With a positive value of m, that follows basically the magnetic field. It's a paramagnetic material in this case. Okay, so it's a finite value of m, which follows, if you want, h. And indeed, for h smaller than 0, you will get just the opposite, so a negative magnetization, because in this way, above Tc, you have a behavior which is paramagnetic. Okay. What happens when t is smaller than Tc? The plot now it's a little bit more complicated, and it works in the following way. So you have a structure which is similar to the one we had before, with a maximum, local maximum, and 2 minima. But actually, you see that in these cases, the 2 minima are not degenerate anymore, and only one of them actually minimizes the free energy. So A divided by n. Okay. and therefore you will have again a finite value of m, which in this case is not degenerate, and for h larger than 0, m is also positive. Okay, the correct value of m. So, as different with respect to the previous case, we have this term here that realizes an explicit breaking from implicit breaking of symmetry. Because now with this term, that is derives from the fact that we have an external magnetic field, which of course breaks the symmetry because it already somehow select the preferred direction. We have a term in the free energy that corresponds to the fact that we have an external magnetic field, and the behavior of the Helmholtz free energy is such that we do not have the generate minima anymore, but just one of them is the correct value of m. Okay. So we have an explicit breaking of symmetry, and actually also the behavior around TC is not critical anymore to some extent. It was already plotted last time when we had a plot of the magnetization as a function of T, and we say last time that at T, for H equal to 0, we have something like this for the magnetization as a function of T, and this DC. Where here, the derivative of m with respect to T is infinity because we have a square root, m scale is the square root of T, of small t. Whereas if H is positive or H is negative, the behavior is something like this. So it's a smoother behavior. So we always have a finite value of m. We do not have a jump, if you want, in the value of m. Okay, for t larger than tc or t smaller than tc. Here we have a jump. We go from m, which is identical equal to 0, to m, which is approaching 0 here, but with a diverging derivative, and here we have a finite value of m without external magnetic field, whereas here the behavior is much smoother. We always have a finite value of the magnetization, and which is driven, if you want, by the external magnetic field. Okay. Okay, I think that with this maybe it's enough. I already stressed last time, well, not so much stress, but I commented on the fact that m is an example of order parameter. And by order, the meaning is just that, the fact that when t is larger than tc, m is equal to 0, and it corresponds to the fact that we do not have any preferred direction, so somehow chaos is dominating the system. Whereas when t is smaller than tc, we pick up some preferred direction, up or down, in this simple example, okay? And if t is equal to 0 instead, we have all of them up or all of them down. Whereas in the intermediate cases, we have some clusters which are up and some clusters which are down, in such a way that the average value of m is not equal to 1, but is smaller than 1, but anyway finite. Okay. Now, let me introduce two of those coefficients, or those two of those exponents that are called critical exponents, that are the following. So we said before that m is the order parameter, which in the case of the Ising model is this magnetization. In other cases could be some other quantity that somehow it's a parameter that tells me in the phase diagram in which phase I am, if you want. I will make another example for the gas, for the van der Waals gas of order parameter. And we say that around the TC m scales as T. Now it's a matter of literature that this coefficient, this exponent is called beta. The exponent that describes the behavior of the order parameter around Tc. Okay, and the scaling was the following with beta equal to 1/2. For what? For two-dimensional Ising midfield. This was the scaling of the order parameter. And this exponent is called by convention beta. Then we have found another thing that was the behavior of the of the magnetic susceptibility, which was a derivative of the order parameter with respect to the external field. And we said that chi of T0 scales as T, and then here again by convention is called minus gamma, where gamma is equal to 1, again in 2D Ising midfield approximation. Okay. So beta and gamma are two examples of critical exponents. They are called critical exponents. And basically, they are the core of the physics of phase transitions, because many different systems can have the same critical exponents, although the interaction are different, the material is different, etc. Okay, they fall in classes of universality, they are called. Now, let me make. So, of course, these critical exponents are describing the behavior of my system close to the critical temperature. Okay. So now we said already that in midfield approximation and two-dimensional Ising model, we have beta and gamma equal to 1. Just to make a comparison, it's good to quote what happens for the exact solution of 2D Ising. Exact solution, and in this case beta is equal to 1 divided by 8, and gamma is equal to 7 divided by 4. Whereas in 3D Ising, and this is a numerical solution, because there is no analytical solution in the case, beta is equal to 0.31 and gamma is equal to 1.25. So you see that when comparing with our midfield approximation, the results, as compared to the exact results, are somehow far away, because here we get 1/2 and here we get 1. And actually, what is good here, well, this approximation starts to be valid for a higher dimensionality, because this 1.25 is 1, and this 0.31 and this 1/2. Okay. So mean field approximation. And actually, the mean field approximation will provide always the same critical exponents, independent from the dimensionality, at least for those cases, these two cases. So mean field works better at higher dimensionality. Now, another critical exponent that one needs to introduce characterizes the behavior of the heat capacity. We have in total 6 critical exponents, which actually are not disconnected. I'm not sure how much time I will have to comment on this year. Anyway, let's make what we manage. So another critical exponent is called alpha, and it describes the behavior of the heat capacity around this heat. Okay. And as before, one writes that the heat capacity scales as, again, the same quantity, which is T, small t, the power of minus alpha, is again by convention. Okay. Where this actually describes the singular part of in the sense that if I have a divergence of the heat capacity, and this is what happens in the two-dimensional Ising model exact solution, one can describe the singular part, so the divergence, with a function which is the modulus of t to the minus alpha. Okay. Now we can try to compute this critical exponent in the case of the one of this mean field approximation for two-dimensional Ising model. Let's sketch the calculation. It's a little bit boring, so I'm not going to do it fully. But the starting point is that CV is equal to T times the second derivative of A with respect to temperature. So this dV, let's compute CV divided by N, maybe. Okay, let's make CV first of all. There's a minus T, second derivative of A with respect to temperature. Maybe I will comment later on where does this equation comes from. Okay, the starting point is that TdS is equal to PdV plus du, and CV is the derivative of u with respect to temperature at fixed volume and fixed entropy. Okay, and I feel that the best way to do it, let me comment this already, is this guy here that we can make u at fixed and okay, I will comment it later. Okay. And the other equation that one has to remember is that A is equal to u minus And from this one can derive these equations. We comment later otherwise. The argument. Okay, so one has to compute the second derivative. Of course, it's very boring, and I'm not going to do it fully. Just to sketch it, the starting point is n divided by n, a divided by n, which was minus a dt log 2 plus epsilon q m squared divided by 2t times t with c plus kb divided by 12 tc to the power of 4 and t to the power of 3 and to the power of 4, which was the expression that we derived before for the expansion around c or around n equal to 0. Because in any case, we want to compute what happens close to Tc. So this is the starting point. Blah, blah, blah. Let me check if at least I'm writing correctly the expression. Okay. Now what happens that one uses the fact that m close to Tc is plus minus the square root of minus 3. Okay. Well, actually, l'ho calcolato below. Just a moment. Minus 3t, 0 from below. Okay. So this for t approaching Tc from below, because above is identically equal to 0. So then one basically takes this expression and puts it here. So m squared is a minus Tc, and n to the power of 4 is 9 t squared. So then one plugs in m squared, this quantity, and to m4, this quantity here, where t is equal to t minus Tc divided by t. So we have an expression that depends just on the temperature and some other constant, and we can make the two derivatives multiplied by t. I'm not going to do it because it's a lengthy and boring calculation, but if you do it, if you try to do it, so basically that's it. What we get is the following. For t larger than Tc, we have that the heat capacity per particle is equal to 0. Why is equal to 0? Because here, for t larger than Tc, m is identically equal to 0. I just have this linear term, and if I do two derivatives, then I get 0. Okay. For t close to Tc, in which case I can use this function here that is valid just close to Tc because it was an expansion. And you have a finite value here, which is equal to 3/2 Tb. And then actually it goes down. But we cannot compute it to this formula because this is valid just at the critical point, the critical temperature. Okay, so then if you try now to realize which is the value of alpha, actually alpha is equal to 0 because there's no singular part. So Cv divided by n is not divergent in the 2D Ising mean field. And therefore, we can this. Therefore, alpha is equal to 0. Actually, it jumps because it jumps from 0 to a final value, which is 3 alpha kb, but there's no divergence on this. Okay. What happens is that in the exact solution for the exact solution, we have a logarithmic divergence. Logarithmic divergence. Okay, in the two-dimensional Ising model. And also for 3D, actually alpha is different from 0. I don't have the value here, but again, we have a divergence that we do not see in mean field. We know that mean field is an approximation, and we can get some qualitatively correct results, but cannot ask too much to this approximation. So this alpha characterizes the similar behavior of the heat capacity around C. Another coefficient, and then maybe we'll stop for a moment, another critical exponent is called delta, and it is the following. Critical exponent delta. And the critical exponent delta basically characterizes the behavior, or well, the dependence from M on the external magnetic field close to TC. Okay. Basically, one writes that M scales close to TC. So for T approaching 0, by definition, as H, which is the external magnetic field, to the power of 1 divided by delta. Okay, this is just a definition of this critical exponent that characterize the behavior, the scaling of M with the external magnetic field at T equal to TC. We can actually derive easily, and then I promise that I will stop, the behavior of M as a function of H in our approximation, because we said before that A divided by N, it has some term which is constant, or in any case independent on M. Then we have a term which was AT minus BC times M squared. Then we have a term which was B M to the power of 4. And then we have a linear term in presence of an external magnetic field, which was minus CMH, where I'm making explicit the dependence on H, which was the coupling, if you want, between the external magnetic field and M. Okay. Now, if I do the derivative of this quantity, now what I have to do is that I have to minimize this quantity with respect to M, so making this derivative equal to 0, and work at T equal to 0. So if I do the derivatives, this implies, apart from this term, I have basically a term which is a 2a m t minus tc plus 4b m to the power of 3 minus ch by deriving with respect to m. If we set now t equals 0, then this term drops. And if I put this to 0, because I have to minimize the free energy, you see that the scaling of m and h is such that m scales as h to 1/3. Okay. Therefore, in our mean field approximation, delta is equal to 3 for 2D Ising mean field. Okay. Can be found easily by this. Now, the real solution, so into the exact solution, is 15, whereas for Ising 3D is equal to 5. So, as before, the critical exponent that we find in mean field approximation approaches the correct one for larger, so for systems with a larger dimensionality. So let's stop because it's 20 already. Sorry, but this part is a little bit longer, and in any way this year I will not complete as possible. So let's stop for 5 minutes. Dunque. Okay, so here I shortly derived the results I was making before. Of course, when computing CV, I have to derive U with respect to V at fixed volume, not fixed entropy, otherwise I get zero. Sorry for that. Yeah, so then, so I just need to fix the volume. And then I can write this as du ds ds dt at fixed volume. Du ds is just t. T ds dt at fixed volume. Then I remember that dA is minus s dt minus pdB. Therefore, minus the entropy is the derivative of A with respect to temperature at fixed volume. Then I can, if I derive S with respect to T, adjust the second derivative of A with respect to T at fixed volume, for which I get the result. Okay. That is the definition of the capacity. So I have to fix just the volume, not the entropy. Sorry. Okay, good. Is it okay? We can remove it. Okay. Now we already described 4 critical exponents, and actually we could compute them within our 2-dimensional mean field approximation for the NP model. Now there are 2 other critical exponents that I want to tell you just for your culture, but I'm not going too much into the details of these. So now the story is the following. So we have 4 critical exponents up to now, which are alpha, beta, gamma, and delta, where alpha is describing the behavior of the heat capacity around Tc. Beta describes the behavior of the order parameter, which in our case is m. Gamma describes the behavior of the susceptibility, which is the derivative of m with respect to the magnetic field. And delta describes the relation between m and h. Okay? It's called the critical exponent associated with the equation of state. It's called of state critical exponent. Now there are other 2 critical exponents that we will not derive, but they are basically connected with this quantity. There is a framework, which is called the Landau-Ginzburg theory, that this year we are not going to explain. Let me see how I write Ginzburg, because I'm not sure. It should be Ginzburg. Let's Ginzburg. Ginzburg. Well, which falls in the topic of statistical field theory, because one has to introduce a field which could be a scalar field, a vector field that characterize my system, which could be the magnetization or some other quantity. So this year we are not going to explain this theory, but within this theory one can compute a quantity that is the following. That is the correlation function. Let's call it P of x, and is a correlation function. Well, 2 points. Correlation function. So basically, this quantity is an ensemble average of the product of the magnetization computed at a certain point and the magnetization at another point. So here by convention I put 0 and x because the difference, so this function will depend just on the difference between the distance, well, depends just on the distance between these 2 points. Okay, so this can be found within this Landau-Ginzburg approximation, and actually the formalism works pretty much. It's very similar. One can write down a field theory with an equation which is very similar to the equation associated with propagation of scalar, massive scalar bosons. So something like the Klein-Gordon equation. I don't know if you've done it in some context. But just with the difference where instead of having the mass of the particle, in this case we have a quantity which is proportional to T. So which is the deviation from the critical temperature. In any case, that's it, that's it. I will not comment much on that, but one can find that phi of x has the following behavior within this theory: is e to the minus x divided by z. Sorry if I write it down in this way, but it cannot do it much better. This guy is called correlation length. And there is an additional x modulus to the minus p. So what does it mean? It means that this correlation function that somehow derived, so somehow it's indicating which is the correlation between a spin, a magnetization at a certain point and another point, scales as an exponential divided by a power law. Now, this exponential, of course, kills everything if the correlation length is equal to, it has a finite value. So we do not expect basically to have correlations between magnetization when we are much far away with respect to the correlation length. Okay, this is what is described with this function today. And now what happens, this is the very interesting part that is and the beginning of renormalization, if you want, in this field, in statistical field theory, is the fact that one finds in this model that the correlation length in turn has a divergence at the critical temperature, because one finds that this C, which is the correlation length, scales as T to minus nu, where nu is equal to 1/2 or infinity. Okay. So then chi, so this, sorry, chi C scales as 1 over the square root of T in midfield approximation. Now, these are results that I'm not going to derive this year. So, but the important point is that when we have a divergence, so this is another critical exponent. So nu is a critical exponent again. Critical exponent for the correlation length. So the important point is that when when we are at t equals 0, which are when we are at t equal to tc, we have a divergence of the correlation length, which means that the correlations between 2 points basically is present no matter how far they are. So it's a collective behavior. So basically, it's like that all the spins are interacting somehow with all the others. Okay, so there is it's called the collective behavior in the sense that I have strong correlations between points that are far away because the correlation length diverges. Okay, and at this point we have the phase transition, so the critical behavior. So the critical behavior is due to the fact that I have somehow that my degrees of freedom have a correlation length, so interact if they want, at scales, so without having a finite value of the correlation length. Of course, the correlation itself somehow will drop as a function of the distance, but with a power law, okay, which is a much smoother way to not to kill the correlation. So if phi is finite, of course, this will dominate, and I have the killing of the correlation at scales equal to the correlation length. Whereas if the correlation length diverges, and this is what happens at the critical point, the correlation between magnetization scales as a power law, which is of course skilled, but in a much weaker way as respect to the case of a finite correlation length. Okay, and indeed, these are critical exponents for correlation length, and the last critical exponent is P. Which is written in terms of another exponent. So I'm not going to ask you those things at the exam, of course, because we are just sketching. And the other critical exponent is theta, which is called anomalous dimension. Okay. So just to make a summary of the critical exponents, so what I was doing here, there are two more critical exponents associated with the correlation function. One of them is the critical exponent of the correlation length, which is called mu, and the other one is theta. And at mean field, let's collect the results. This is 0, this is 1/2, this is 1, this is 3, this guy is 1/2, and actually this theta is equal to 0. Okay. That's enough for what concerns the critical exponents. Well, I'm not sure if next week I'm going to explain you the scaling. I have to think about that. Okay, so if we continue on this part, or if we do something different, which is more related to the fluctuation dissipation theorem, I will see what to do. Okay. The correlation length explodes, so that means that we have correlations. We don't have a typical scale for the correlation of 2 points, the magnetization 2 points. One has the idea of making a transformation of spin of blocks of spins that maybe I will describe next week, but I'm not sure I will do it. So I will think about that. So now for the rest of the time that we have, let's make just some, I have here something that belongs to another chapter of statistical physics, which is the matter of fluctuations. And let's just make short exercise in the rest of this time, though I'm not sure we can do it. Then I will decide next week if going on with the critical exponents or instead going on with the fluctuations. I will see. Questo è blu, facciamo il verde, facciamo il rosso. So another chapter of statistical physics is the one regarding the fluctuations. So somehow it's something that allows us to go beyond the thermodynamical limit and see what happens in physical systems, finite physical systems. Now, this topic is also very wide, so I'm not sure how much we are going to do, but let me make just an exercise today in these 10 minutes that are left. And so using statistical physics to find the role of fluctuations. So suppose that we have, so this is an exercise, N0 particle in a box of volume V0, is a volume, and ask ourselves which is the probability to find N particles in a volume V. So the probability, which is a function of V and N, or N V, of finding N, which is less than N0 particles within a volume V, where V is smaller than N0. Now, if I have to write a probability to find one single particle in a portion of V, well, in a volume V, the probability would just be for one particle, V divided by V0, no? For one particle. For N particles, the probability would be times N. And this probability must be multiplied by the fact that I do not have, well, the rest of the particles are in the, if you want, in the other part of the volume, no? So it's V minus V0, and that is N. What I'm going to write is a binomial distribution, okay, that I will comment in a moment. And here I have the combinatorial, which is N factorial divided by, sorry, N0 factorial. N0 is the number of particles, divided by N factorial and N0 and okay. So let me comment on this. So I'm asking myself, which is the probability of finding N particles in a volume V, where N is smaller than N0 and V is smaller than V0. So this is the number of picking up N0, N particles from N0, which is the binomial coefficient. This is the probability of finding N particles in the volume V, and this is the times the probability of finding, if you want, the rest of the particles, which is N0 minus N in the rest of the volume. Okay. So now we can find, so this is general, okay? So now suppose that we want to compute the probability of not finding the particles in a volume V. So let's take n equals 0 and finite value of b. So, which is the probability that we are asking ourselves of not finding particles in a certain volume b. We just need to put n to 0 there, and for I get so this guy here is just 1, and this is 1 minus v divided by v0, and then it is here, this is to the power of n0, which if v is smaller than v0 is an exponential, and is e to minus n0 times v divided by v0. Okay. Now, suppose that now we want to work a little bit with scales. Suppose that we have a box with a volume which is 1 meter cubed. So, square root of v0 is equal to L, and suppose that this is equal to 1 meter squared, 1 meter, sorry, 1 meter. And suppose that we, well, v 1/3 is equal to the length L, and suppose that this is equal to 10 to minus 8 centimeter, for instance. And of course, m 0 is of the order of the Avogadro number, so 10 to 23. Now you see that if a scale for which I'm asking, which is the probability that is empty, and if the scale is such small, then this probability is not so bad, in the sense that for those numbers, this probability is exponential of minus, here you have 10 to 23, which is n0, and then v divided v0. Well, v0 is 1 meter cubed, and this 10 to minus 8, not centimeter. Sorry, this let's make meter, otherwise it's useless. And then this 10 to the minus 24. Okay, minus 24. 23 minus 24, okay, is not so, sorry, 10 to 23, yes, and then this 10 to minus 24, because I have to make the cube of this, okay. So this exponential of minus 10 to the minus 1, no? Which is, you know, a respectful number, okay, so different from 0. Now I will make it explicit what I mean different from 0. Suppose that now that I'm using, instead of a scale of 10 to the minus 8 meter, which is 10 nanometers, if L is equal to 1 centimeter, which is 10 to the minus 2 meters. So in this case, if I'm not mistaken, I should get, so for 1 centimeter, which is 10 to the minus 2 meters, okay, I should get, that the probability now is e to the minus 10 to 17, which comes from 23 minus, is the power of 3 is minus 6, so 23 minus 6. Okay. So this is basically, you know, so it's basically 0. So that means that the probability of finding empty a space of 1 centimeter is basically 0. So fluctuations are important and are somehow doing something when the scales are of the order of the 10 to the minus 8 or even smaller. Okay. So for macroscopic scales like 1 centimeter, for instance, fluctuations like the one that I'm going to describing, so having a part of empty space is basically impossible. And impossible means this number here, which is a very large, but very small number. Now, similarly, we can ask ourselves which is the probability if I have a box of a certain volume to find, of course, is a similar calculation, to have a situation in which, suppose that we have a box here filled with particles in thermodynamical equilibrium, and now suppose that for a certain fluctuation that can occur, because everything can occur, of course, we are in a situation in which half of this volume is occupied, the other half of this volume instead is empty. Okay, it is a fluctuation that could happen, but which is the probability of this fluctuation? Well, it's 0, and then here instead of p, I must put b0 divided by 2. Okay, so this is empty. Now, using the previous formula, I just have the previous formula, so n is equal to 0 again, and I have e to the minus e to the minus n0 times b divided by b0, which in this case, since b is equal to b0 half, is n minus n0, and this is the log log of 1/2. Sorry. So this is minus n0, this is 1/2. Okay, 1/2. Scusate, ma qui mi sembra che mi sono perso. Let's do it in this fashion. So here I had 1 minus this b0 divided by 2, and this is b0, now to the power of n0. So let me start from scratch. So this is b0 cancels, so I have 1/2 to the power of n0, okay. And this is also equal to exponential of n0 times the log of 2 with the minus. Okay. Minus n0 log of 2. Now, of course, this log of 2 has not an important role, and you see that the probability scales as e to the minus n0, which again is a very small number, because n0 is of the order of 10. Okay. We can compute the probability. This probability can be computed in another way, because if I have a situation like this as a starting point, and I ask myself which is the variation of entropy that I have from this situation in which half of the volume is empty, and this situation in which I have a free expansion of my particles occupying all the volume, which is the variation of entropy that I have in this case for a free function. Well, one can use the formula of variation of thermodynamics, and basically, well, I get the delta S is equal to n kb for a perfect gas logarithm of 2. Let's put n0 here. N0 kb log of 2. This can be done by realizing that t here is constant. Okay. Now, this is the variation of entropy that I have from here to here, and I also know that the entropy by Boltzmann is kb logarithm of omega, where omega is the number of microstates associated with my macrostate. So from here, I find that omega is equal to exponential of s divided by kb, and therefore now if I consider the variation of omega as due to the free expansion, then this will be delta s divided by kb, and delta s is this number here, n0 kb log of 2. So this e to n0 log of 2. Okay. So this is from this situation, half of the volume empty, to this situation here, all the volume occupied. So if I do the opposite, from occupied to half of the volume empty, we should have the same variation of entropy, but now negative. Okay, and so here the delta omega is equal to e to the minus n0 log of 2 as before. So somehow such a fluctuation, it's very improbable, and also can be seen as a variation, a fluctuation of the entropy, which is of course ridiculously small. So in the sense that the phase space must be reduced by this factor e to the minus n0 of 2, but n0 is a very large number. Okay, so such a 11, such a fluctuation is completely negligible because of those numbers. In principle, one can find also how much time we need to wait until these fluctuations happen. And because of this number, basically, we find the values are of the order of 10 to 23, exponential of 10 to 23 seconds, which of course is a very long time. Okay. So I guess the next time we will continue with this topic, which is about fluctuations, if I do not change my mind. And we will see the Einstein relation for the diffusion process. So let me stop now because it's 11, and see you.